This is Unit 13, Lesson 5, Sampling Distributions. We'll be covering pages 464 to 466. It'd be helpful if you had a calculator for just adding, subtracting, multiplying, dividing purposes, and a highlighter. Homework is pages 467 to 468. This first page on 464, you're welcome to just stop the video and read it on your own and then fast forward through the video. But there's some important information here, so please just make sure if you're not following along with me reading it that you do read it on your own. So in the last lesson, we saw how the data from samples of a population allows us to find an interval in which we are 95% confident that the actual population data value lies. Conversely, we can start from known population data and develop an interval in which we are 95% confident that samples from the population would fall. We will call this our 95% confidence interval, which I simply abbreviate confidence interval as CI. The only way to be 100% confident of the population data is to collect data from the entire population. Since this usually is not feasible, we use data from samples to be sure enough about information to move forward. Why 95% and not some other percentage? Being 95% confident means there's a 5% chance that the true population value is outside the confidence interval. If we used something bigger like 99%, we would be more likely to include the true population value. At the same time, if the confidence interval is really large, it could lose its meaning to help us find an estimate of the population value. On the other hand, if we used a smaller, like an 80% confidence interval, for example, we could narrow the range of values in the confidence interval, which would give a more specific estimate. But then there's a 20% chance of missing the true population value. What is the balance between the above two issues? Both have their positives and negatives, just like most meaningful decisions in life. The percentage for the confidence interval can be different than 95%, but 95% is the most common choice in statistics to balance the above two possible complications. It is the one we will always use in Algebra 2. So we will always use a 95% confidence interval. And we know how to get that, right? The 95% confidence interval is equal to the mean plus or minus 2 standard deviations. And standard deviation, sometimes I abbreviate SD, or we can also just leave it as SX. To summarize, inferential statistics is a field of math that helps us move forward, making decisions with confidence, given some uncertainty. This is why statistics is a required course for medical fields, business, psychology, some education courses, and mathematics, etc. It is why statisticians can get a job virtually anywhere. Sample means. Single samples can find an average or a sample mean instead of a sample proportion. Exercise number 1, take a sample of 10 heights in your class and find the mean of the sample. So, of course, we can't do that. So I just took some 10 heights and put them in, and this is inches, so 64 inches would be equivalent to 5 feet 4 inches, 60 inches 5 feet, etc. And I could simply take and find the mean. Let's try stat calc, 1 bar statistics, right? And this mean, the average for this sample of 10 heights is 66.7. So, and then more samples can be taken, and the mean of each sample can be placed in a dot plot, and we would have the sampling distribution of sampling means. Exercise number 2, exploring sampling distributions. So I'm going to show you sampling distribution on AlgII.com. And we want to answer these 2 questions. What happens when we change the sample size? And what happens when we increase the number of trials? I'm here at AlgII.com. We're going to look at sampling distribution mean. I'm going to change this percent with internet access to NFL contracts in the year 2015. Okay, so on the right-hand side, the actual population. So in the year 2015, of the 2,099 NFL players, the mean salary was $2.238 million. Now let's keep in mind our 2 questions. What happens when we change the sample size? So choose sample size of 30. So sample size right now is set to 10. So I'm going to change that to 30. And I'll generate 100 samples. So we have 100 dots down here, and each dot represents the average or mean of the salaries for 30 NFL players. So because each sample is a size of 30. And notice the mean here. So this is the mean for the 100 sample distribution. So it's 2.32, which is close to the 2.238, which is the population mean. The standard of error, this is what we want to focus on here. Standard of error here is the same as our standard deviation. So the standard deviation is 0.630. Let me just generate another 100 samples. And the mean is still about as close to the population mean. The standard deviation is 0.588. And we see here we have a bit of a mound shape. Now, let's change the sample size from 30. Let me change it to 100. Because our first question is, what happens when we change the sample size? I'll generate 100 samples. And the mean for this distribution of 100 sample means is still close to the population mean. But the standard deviation here is 0.283, whereas before when we had a sample size of 30, we were at like 0.63 and 0.588. Okay, so let me just take another 100 samples, and the standard deviation again is down. It's 0.287 as compared to the 0.588 and 0.63 we had with the sample size of 30. All right, so what happens when we change the sample size? Well, the larger the sample size, as we increase the sample size, the standard deviation gets smaller. So as we increase the sample size, the standard deviation decreases. Next question was, what happens when we increase the number of trials? So right now I'm up to 200 trials, and I've got this sort of, mound shape. So let me generate 1,000 samples. So now we're up to 1,200 samples. And we definitely have much more of a, I would call this more of a kind of a hill. Let me go one more 1,000. So we're up to 2,200 samples. This is definitely resembling our normal distribution curve. And if I want to go even more, so this shape here is a normal curve shape. So you see that when we change the sample size, right? When we increasing the sample size decreases the standard deviation. Increasing the sample size decreases the standard deviation. What happens when we increase the number of trials or the number of samples that we take? The dot plot more closely resembles the normal curve. It does not matter if the original data was normally distributed. This will always happen. So it does not matter whether or not the original data was normally distributed. Data was. This will always occur. The dot plot will more closely resemble normal curve when you increase the number of trials. Okay, a new term, the margin of error. You have to memorize this. The margin of error of a sampling distribution is the distance from the mean to one end of the confidence interval. The margin of error can also be calculated by multiplying the standard deviation by 2. So for margin of error, it's simply 2 times the standard deviation. Margin of error multiplying the standard deviation by 2. So margin of error, sometimes you'll see it abbreviated MOE for margin of error. Sometimes I might do just simply ME for margin of error. But the margin of error is equal to plus or minus 2 standard deviations. And again, with standard deviation, it can be abbreviated SD or the SX. So given the mean, X bar, and the standard deviation, XX, the margin of error is plus or minus 2 times the standard deviation. And the confidence interval is the mean minus 2 standard deviations to the mean plus 2 standard deviations, or what we've also seen, the mean plus or minus 2 standard deviations. This is our confidence interval. You have to know this. You have to memorize that. And the same with the margin of error. Plus or minus 2 times the standard deviation. If you're given the confidence interval from A to B, like here we have our confidence interval from A to B, here's a visual, and you want to find the mean, well, the mean needs to be midway between those two. It has to be the average of those two. So you would take your B plus A and divide by 2. And to find the margin of error, you would take B minus A and divide by 2. So let me just point out here that right here is the mean, right? It's at the center. A and B represent the ends of your confidence interval. The +1 is for 1 standard deviation above the mean, and the B value would be at +2 standard deviations above the mean. And the A value would be at -2 standard deviations, so 2 standard deviations below the mean. Starting from the mean and standard deviation, what do we want to find here? Well, we want to find the confidence interval. So we know that when we're given the data measurements here, our confidence interval is equal to the mean plus or minus 2 standard deviations. So 0.43 plus or minus 2 times 0.06. Well, 2 times 0.06 is 0.12. And keep in mind that this here would represent the margin of error. So 0.43 minus 0.12 is 0.31. And 0.43 plus 0.12 is 0.55. So this is our confidence interval. Visually, if you look at it as a picture, all right, here would be our mean of 0.43, and we'd have to add 2 standard deviations to get to the upper end of our confidence interval. So 2 times 0.06 we get 0.43 plus 0.12 is 0.55, and we'd have to subtract 0.43 minus 0.12 is 0.31. So algebraically, or if you find it more helpful to visualize it, and just again keep in mind that 2 times the standard deviation, the 0.12 here we get, is if we put a plus or minus in front of that, that is our margin of error. So our margin of error is, we should add an equals there, margin of error is equal to plus or minus 0.12. Now starting from the confidence interval, so if we're given the confidence interval, well, what's the mean and what's the margin of error? Well, we know the mean has to be the average of this. It's got to be in the middle of that. So we add 0.31 plus 0.55 and divide it by 2. So that's 0.86 divided by 2 is 0.43. So that's our mean. To find the margin of error, well, I can simply take the mean and subtract 0.31. Or I could take the upper portion of our confidence interval and subtract the mean. So it's either this is our A value, this is our B value. So I could take our B value and subtract the mean. So 0.55 minus 0.43 is 0.12. And we add a plus or minus to that. So our margin of error would be plus or minus 0.12. Again, visually, if you have 0.31 to 0.55, the mean we know has to be the middle. It's got to be the average of these two. So we add them, get 0.86 divided by 2 is 0.43. So if our mean's 0.43, then our margin of error is the distance from the mean to our upper interval, which is the same as the distance from the mean to the lower interval, the lower value of our confidence interval. So 0.43 plus what would bring me to 0.55, and that's 0.12. And we have another 0.12 this way. So our margin of error is plus or minus 0.12. Now exercise number 3. In each of the following situations that resulted shows the results from a sampling distribution. Use the given information to fill out the table. So we have the mean, the standard deviation, the margin of error. Remember, the margin of error is equal to plus or minus 2 standard deviations, and our confidence interval from A to B. And our confidence interval we get, that is the mean plus or minus, I should say CI equals the mean plus or minus the margin of error. But again, margin of error is the same as 2 standard deviations. Okay, so for A, our mean is 6.1, our standard deviation is 2.0. So our margin of error is equal to plus or minus 2 times the standard deviation. So it's plus or minus 2 times 2.20, which is simply plus or minus 4.0. The confidence interval, and if you don't know the formula for a confidence interval, then please write it down. It's going to be the mean, which is 6.1, plus or minus. I can either do 2 times the standard deviation, or I can do the margin of error, plus or minus 4.0. So if I subtract 4.0 from 6.1, I get 2.1. And if I add 4.0 to 6.1, I get 10.1. So our interval is 2.1 to 10.1. For B, we have the confidence interval is 100 to 190. So again, if you're a visual person, you can do 100 to 190, and the mean here has got to be in the middle. So add 100 and 190 and get 290. So the mean's going to equal 100 plus 190 divided by 2. 290 divided by 2 is 145. So the mean is 145. And if I'm thinking, oh, the mean's 145, then what's the margin of error? Well, 145 plus what would bring me to 190? 45. Or I can say 145 subtract what would bring me to 100? 45. So the margin of error is equal to plus or minus 45. And the standard deviation, well, 2 standard deviations equals the margin of error. So the standard deviation would be the margin of error divided by 2. 45 divided by 2 is 22.5. So our standard deviation is 22.5. Our margin of error is plus or minus 45. And our mean was 145. You're certainly welcome to try C and D. Pause the video, try C and D on your own if you want. Okay, so here the mean is 0.32. The margin of error is 0.15. Well, if the margin of error is 0.15, then the standard deviation. So standard deviation equals 2 times No, 2 times the standard deviation is the margin of error. So the margin of, excuse me, standard deviation is half of this, just like I did up here. .15 divided by 2. 0.075. That's our standard deviation. Our confidence interval is going to be the mean plus or minus the margin of error. So the mean is 0.32 plus or minus 0.15. 0.32 minus 0.15 is 0.17. 0.32 plus 0.15 is 0.52. Nope, 0.47. Okay, so here are intervals 0.17 to 0.47. And for D, we have the confidence interval is given 0.62 to 0.70. So right away, I would just find the mean has to be in the middle. So that's got to be 0.66, right? Yeah, 0.66. So the mean is going to be 0.62 plus 0.70 divided by 2. And just throw that into the calculator. 0.62 plus 0.7 divided by 2, 0.66. So our mean is 0.66. And if I, again for the visual, if I have 0.62 and then a mean of 0.66 and then in the upper end of our confidence interval is 0.70, then the margin of error is, well, if I add 0.04 rather, that'll bring me the 0.70. So our margin of error is 0.04 plus or minus 0.04, and the standard deviation has to be half of that, 0.02. Okay, now the last thing, finding a confidence interval when we have a dot plot or histogram, but no statistical measurements. So you are looking for a 95% confidence interval. So cross out 2.5% of the data in each tail. Note, we only do this when we do not have statistical measurements. The only time we cross off 2.5% from each tail is when we do not have statistical measurements. So when the mean and standard deviation are not given to us. So exercise number 4 says estimate a confidence interval, a mean, margin of error, and standard deviation for each of the following dot plots. So we have a sample means from 50 samples. So there are 50 dots here. So we want to cross off 2.5% of our 50 dots in each tail. So number of dots to cross off in each tail, we would take 2.5% of the 50 in our sample. So there's 50 dots here. Well, change the percent to a decimal, it's 0.025 times of means 50, so 0.025 times 50 is 1.25. So we want to cross off 1.25 dots from each end of our data distribution here. Well, 1.25 would round down to 1. So on the right-hand tail, we cross off 1, and then on the left-hand tail. So now our estimated confidence interval is from here to here. And let's see, if this is 5, 4, 3, 2, 1. So this is 3, and this is 10. So our estimated confidence interval is 3 to 10. The mean needs to be midway between that. So the mean is going to be 3 plus 10 divided by 2. 13 divided by 2 is 6.5. So the mean is 6.5. The margin of error, and for those of you who are visual, if I put the mean of 6.5, well, 6.5 subtract 3.5 brings me to 3, and 6.5 plus 3.5 brings me to 10. So remember, the margin error is the distance from the mean to either the upper end of your confidence interval, which is going to be the distance from the mean to the lower end of your confidence interval. So what did I say? That was 3.5. Don't forget the plus or minus. And the standard deviation is half the margin of error. So 3.5, so I'm thinking $3.50 divided by 2 is $1.75. So our standard deviation is 1.75. B, here we have sample proportions from 1,000 samples. So there are 1,000 dots here, right? 1,000 dots. Yeah, and notice we have 1,000 samples, so this is representative of a normal curve here. Resembles a normal curve. That's the cutoff on each tail. We want 2.5% of 1,000, which is 0.025 times 1,000, which is 25. So we have to cross off 25 dots on the left tail and the right tail. So go ahead and count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. Okay, so I'm here. And then crossing off 25 from the right tail. And here. And we're rounding to the nearest hundred, so our estimated confidence interval is, let's see, 51 or 0.51 would be about here, so we're definitely closer to 0.52. Right? 0.51 would be about there. So our estimated confidence interval is 0.52 to 0.60. The mean has to be in the middle of those two, right? So I can add them. 0.52 plus 0.60 divided by 2 is 0.56. And now you don't have to show this work if you don't want to. So the mean is 0.56. The margin of error, 0.56 minus 0.52 is 0.04. So I'm going to take, I'm going to say it's the mean minus the lower end of our confidence interval, 0.04, but let's not forget plus or minus. And the standard deviation is half the margin of error. Okay, so we've finished with the notes. There is going to be just a short visual clip of two more confidence intervals, estimated confidence intervals using Lock5 stat. And your homework is the 2 pages 467 and 468, which are very similar to the lesson. Again, thank you for your attention, and I hope you have a wonderful day. I'd like to provide you with another visual for exercise 4 on page 466. Going back to our NFL contracts, and if I generate 1,000 samples, what we have here is we have 1,000 dots, and in red here we've got 25 dots in the left tail that are crossed off, and 25 dots on the right tail that are crossed off. The only time you use this crossing off or crossing out the dots is when the actual statistics measurements are not given. So suppose this data or information in the upper right-hand box was not given to you, but you know that there are a sample of 1,000. We would take 2.5% of 1,000 is 25. So then we cross off the 25 dots on the right-hand tail and 25 on the left-hand tail. So now that leaves us with an estimated, this is estimated, confidence interval of 1.29 to 3.325. And let's suppose I reset this and generate 100 samples. So if I'm generating 100 samples, then 2.5% of 100 is 2.5. So we'd have to cross off 2.5 dots on the right tail and the left tail. But since we can't really cross off half a dot, what was done here is that in the right tail, 2 dots were crossed off, and in the left tail, 3, leaving an estimated confidence interval of 1.319 to 3.390.